In this video, we're going to look at the continuity of functions with several variables. And we're not going to spend a ton of time on it, but the idea is we need to be able to, we'll need to be able to look at a function with two or more variables and pretty quickly decide if it's continuous or not, so that when we do derivatives and integrals and things like that, all of those results that rely only on continuous functions will apply to the function that we're working on. And so just really quickly, we've just talked about limits, so it's pretty easy to define what it means for z equals f of x to be continuous. So we're going to define this function to be continuous at the point AB. And so remember, these functions are defined on points in the plane, so it has to be continuous at this point. If the limit as xy approaches 0, or approaches AB of this function f of xy is equal to the function value f of AB. All right, this is the same definition for continuity of one variable functions and same definition as the continuity of vector functions. So we want the limit equaling the function values. Right? So some basic facts about continuity. So we, just like in one variable calculus, polynomials and rational functions, right? These are in two variables, are continuous when defined. Right? So polynomials are always continuous because they're always defined, but rational functions, we might have a division by zero issue. So as long as they're defined, these will be, those will be continuous. Trig, exponential, log functions of all kinds will be continuous when defined. Right, so some of those are always defined, like exponential functions and sine and cosine. Others are only defined in certain regions, and so those will be continuous as long as those are defined. And if we combine continuous functions using sums, differences, products, quotients, or composition. So these things of continuous functions are also going to be continuous when defined. Right, again, the quotient of two functions might not exist everywhere because we, again, might have a division by zero. But these are all basic facts that usually are justified in a Calc 1 course, at least for one variable functions, and they extend in the most obvious way to two variable and more variables as well. Right, so for a quick example, let's consider this function, f of xy equals the sine of x plus y, all divided by x squared plus y squared minus 25. Right? And so what we want to do here is determine where this function is continuous. All right, and so if we just kind of look through all of our various rules, in the numerator, we don't have any problems. X plus y is a polynomial, so it's continuous. Sine is a function that we know is always continuous. And so the sine of x plus y is a composition, and that is also continuous. So the numerator is continuous everywhere. So is the denominator. The denominator is continuous because it is a polynomial, x squared plus y squared minus 25. So the only problem here might come from the division, the rational function part of this particular function's makeup. And so we know from just looking at this function will be continuous everywhere except when that denominator equals 0. So it's not going to be continuous when x squared plus y squared minus 25 equals 0. We can rearrange this to say x squared plus y squared equals 25. And so it's not continuous when we are on this circle. Right? This is a circle in the plane. It's centered at the origin with radius 5. Right? So this particular function is continuous everywhere except on that circle that's centered at the origin with radius 5. Right? Everywhere else, this function is continuous. So let's say we wanted to do the same thing with this function. So f of xy would be e to the negative 3xy squared minus 4y squared. Now notice all of that is in the exponent of the exponential function e. Right? So this function, if we look at it quickly, we see that the exponent is a polynomial, negative 3xy squared minus 4y squared, so that exponent is always continuous. And we know that e to the x, or e to the z, whatever we want to call that, that's always a continuous. And so this is a composition of two continuous functions. Right? So this function would be continuous everywhere, right, in the entire plane. And we'll look at one more example. So let's say f of xy was the arctangent of y over x plus the natural log of the absolute value of y minus x. All right, well, this function f is the sum of two separate functions. So we know the sum of continuous functions would be continuous. So we're just going to look at each of these functions separately and determine where they are continuous and then combine the results together. So we know the arctangent function is continuous everywhere. And so the only place this is not continuous will be when y over x is undefined. And the only place where y over x is undefined is when x is equal to 0. All right, so when x is equal to 0, we have the arctangent of an undefined amount, which is undefined. But anything else will work. If x is not 0, then y over x is a real number, and we can find the arctangent of any real number. And there's no continuity issues there at all, except for at x equals 0. With the natural log is continuous wherever it's defined, and it's defined for positive values. Right? So we cannot have the log of 0 or the log of a negative number. Now the fact that we have the log of an absolute value tells us that we're never going to get the log of a negative number. The thing we're taking the log of will always be non-negative. But we could end up getting log of 0. And so we want to avoid that. And so we want y minus x. We want to exclude any value where y minus x is equal to 0. Right, which means we want y to not equal x. Right? So if we just combine these two facts together, this particular function will be continuous at any point when x is not equal to 0 and y is not equal to x. Right? So as long as x is non-zero and y and x are not identical, this particular function will be continuous. So before moving on to derivatives, which is the next step in our calculus development for multivariable functions, I want to talk just a little bit about functions with more than two variables. So functions of three or more variables. Okay. Once you're comfortable with the idea of a function of two variables, extending this to a function of three variables is nothing significant. And the idea now, if we have a function of three variables, is that our function is defined as an expression with three different variables, and our inputs to our function, our domain, will be a point in three-dimensional space. And so for example, if I have a function defined f of x, y, z equals xz divided by 2y squared plus z to the fourth, right? This would be a function of three variables. We have an x, a y, and a z. And so in order to evaluate this function at some point, we would have to pick three input values. So for example, if I wanted to compute f of -4, 2, and 1, right, this would just simply be -4, that's x, times z, which is 1, over 2y squared, so 2 times 2 squared, plus 1 to the fourth. All right, and then we just simplify all of this. So this is going to be -4 divided by 8 plus 1. So we get -4 ninths. Right? All right, so this function behaves exactly like the function of two variables, except that we have three. All right, we could, of course, have four variables. So for example, if I had a function f of t, u, v, and w, and we define it as 4t minus v to the w power divided by u squared plus 3. Right? This is a function with four variables. And so we could compute f of 1, 2, 3, 1. We just have to pay attention to which variable is which. So this would be 4 times 1 minus v, which is 3, raised to the w, which is 1, over u squared, so that's 2 squared plus 3. And so we get in the numerator, we have a value of 1, and in the denominator, we have 4 plus 3, which is 7. So f of 1, 2, 3, 1 would be 1/7. And so everything that we've really done with functions of two variables can be done with functions of three variables, except for we don't have the ability to graph these particular types of functions. For three variable functions, to graph them, we would need 4-dimensional space, and for four variable functions, we would need 5-dimensional space, and neither of those things exist in a way that we can realize them visually. And so we really don't have any kind of graphical approach to these, but we can certainly compute limits in the same way that we did with functions of two variables. We're going to approach a particular point in 3 space along some path in 3 space. We can talk about the functions being continuous, meaning the limit equals the function value. And when we do derivatives and integrals coming up, we're going to be able to approach them the same way. They just won't have the physical meaning that we're used to having in calculus, because we'll be looking at things in higher dimensions than the space that we live in.